right, welcome back to Honors College Algebra students. Today we're going to start a brand new unit called Radicals, and this first section of the unit is called Radical Basics. So for a warm-up, we're going to list the perfect squares, perfect cubes, and perfect fourths. For example, because 1 squared is equal to 1 and 2 squared is equal to 4, that makes 1 and 4 perfect squares. So if you did 1 squared, you'd get 1. If you did 2 squared, you'd get 4. 3 squared is 9, and so on. 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared, 11 squared, and so on. Now, it'd be good to have this list handy for our lesson here. Now let's think about perfect cubes. So if we had 1 cubed, we'll get 1. If we have 2 cubed, oops, let's make that a 3. If we have 2 cubed, that would be equal to 8, and so on. So the first perfect cube is 1, the second perfect cube is 8, and so on. Okay, and then the same thing goes with fourths. So if you said 1 to the 4th, that equals 4. If you said, what's 2 to the 4th? And remember, 2 to the 4th means 2 times 2 times 2 times 2, or 4 times, right? So you're getting a much bigger number, which is 16. Okay. Let me correct this. 1 to the 4th is not 4. 1 to the 4th is 4. Sorry, 1 to the 4th is 1. Okay, so perfect fourths would be 1, 16, 81, 256, 625, 1296, 2401, and 4096. Now, obviously, if it's fourths, it's climbing quicker, right? And so on. All right, let's look at the parts of a radical. The little number that's inside the radical sign is called the index. Now, when there is no index, it's implied, like for square root, the 2 is implied, you don't write it. But if it's the cube root, you would write the index. All right, the little check mark or little sign itself, that's called the radical sign. And the thing underneath the radical sign is called the radicand. So it says here, like I said, with the 2 being implied, if there is no index, it is assumed that the index is equal to 2. Because you know, when you see the square root of something, you don't usually see a 2 index in there because it's implied, like they say. Okay, so that's kind of the basics. Now we're going to go to the number of roots, possible roots. So it says here, give all possible roots to the radicals below. So you have to think in terms of signs, like plus or minus. So the square root of 16 is 4, you guys know that, but it could be a positive 4 or it could be a negative 4. And the reason why is because the reason why the square root of 16 is positive 4 is because 4 squared is equal to 16. But also, if you take a negative 4 and square it, you also get 16. So you have to consider all possible roots. So the square root of 121 would also be plus and minus 11. 289 would be plus and minus 17. And the square root of 4 over 25 is the same thing as the square root of 4 over the square root of 25. We'll learn a little bit more about that. But because both of these are square roots, we have to say that this is plus or minus, the square root of 4 is 2, and the square root of 25 is 5. Now, when we get to, this is what we call an even root. Also, the fourth root is going to be an even root. Let me stop sharing just for a minute. There we go. Okay, so this is also an even root. So only for even roots do you have to worry about the plus or minus. So the fourth root of 1 would be 1, since 1 to the fourth root is equal to 1, but also negative 1 to the fourth root is also equal to positive 1, right? Because if you multiply something an even number of times, you're going to get rid of all the negative signs. So for any even root, you're going to have plus or minus as your final answer. But for an odd root, you only have to worry about the positive answer, or negative answer, I should say. So this is an odd root. I'm trying to make this neat for you. All right, so the cube root of 8 is just positive 2. The cube root of 343 is just 7. And the reason why is because 7 to the third power, or 7 times 7 times 7, is 343. Now, when you have an odd root of a negative number, the answer will always be a negative. So the cube root of negative 125 is negative 5, right? And the reason why it's negative 5 is because negative 5 to the cube to the third power is equal to negative 125, which makes sense, right? Because you have a negative times a negative, that's a positive, times another negative would make it negative. And then the cube root of negative 1 over 27 is the same thing as the cube root of 1 over the cube root of 27. Well, the cube root of 1 is just 1. And remember, when you take the cube root of a negative number, the answer will always be negative. So we've got negative 1 over the cube root of 27 is just 3. Now, what I'll do with this lesson is post what 2 squared, 4 squared, 5 squared, you know, all of that is for square roots, cube roots, and fourth roots. All right, so the fourth root of 1 is just going to be 1. The fourth root of 2401, if you look back to our original warm up there, that was the 1, 2, 3, 4, 5, 6, 7th. So that would be, let's see, where are we? 2401 would be plus or minus 7. Since 7 to the fourth power is 2401. But also negative 7 to the fourth power, since it's an even power, is also equal to 2401. If you take the fourth root of 4096, you'll get plus or minus 8. And then the fourth root of this we're going to break up into numerator and denominator. So we can say the fourth root of 81 over the fourth root of 16 is the same thing as plus or minus. Fourth root of 81 is 3, and the fourth root of 16 is 2. So your answer is plus or minus 3/2. Okay, now let's summarize some other characteristics here. If you have an even index and a positive radicand, remember that's the number under the radical sign. So even and positive, you're going to have what we call real roots. So they'll be real numbers. And that happens for all of these other situations as well. All right, so for even, you can have 2 possible roots, and that's because you have to have the plus and minus for even roots. If you have an odd index and a positive radicand, then there's only 1 root because it's only the positive, right? So if you take the odd root of a positive number, if you take the odd root of a negative number, again, you're just going to have 1 solution, and it would always be the negative solution. Now, if you take the even root of a negative number, what you're going to get, let's say this is the square root, which is an even square root, and we'll just put the index here so you understand it's even. The square root of negative 16. Well, you guys know from our study of imaginary numbers that this can be simplified to the square root of negative 1 times the square root of 16, which is equal to 4i. So the type of roots you're going to get if you take the even root of a negative number is an imaginary number. Type of root means type of, simplification, what the final answer would be. And you're also going to get, because it's even, just like you got in this case because it was even, you're going to get both the plus and minus. So I really should have said this is plus minus for I. You'll get the hang of it, though, the more you work with it. All right, our next topic is to figure out how to simplify radicals. So the easiest way to simplify radicals is to do what we call a factor tree. So if you figure out, well, what are some factors of 117? Well, one factor of 117 is 9. Another factor of 117 is 13. And then if you break 9 down, so now these are all prime numbers, then since you've got a pair of 3s, one 3 comes outside the radical. And since 13 doesn't have a pair with it, that has to stay inside the radical. All right. So for number 2, I'm going to do the factor tree down here. 300. Let's use a different color just because we can. 320. So that's 32 and 10. And to get to know this one, 32 comes up a lot. This you can break up into 5 2s. And you can do that because 32 is 2 to the 5th power. That'd be a good one for you to remember. And then 10 can be breaking up as 2 and 5. So let's look at the pairs we have first. And first, I also want to bring this 4 outside down. Anything I bring out, I'm going to multiply by that 4. So I've got 1 pair, 2 pair, 3 pairs of 2s, right? So that would be 2 to the 3rd power. And then the number that's left is the 5. So that's got to stay inside the radical. And then when we simplify that, we'll get 4 times 8, which is 32 on the outside. So we're just going to simplify this to get 32 root 5. So the idea here is to get all of the perfect square factors or any pairs out from underneath the radical sign. All right, let's try another one here. Let me mark that this is number 2. All right, let's see. I'm going to give you a slightly different way to think about this. You could rewrite this as, I know that 6 times 8 is, I'm just bringing the 2 over. 6 times 8 is 48, right? So you could rewrite this as the cube root of 8 times the cube root of 6. Now, the reason why I wrote that like that is because I know that 8 is a perfect cube. So it'll save me some time from doing factor trees. So here's the 2 that was on the outside. And then the cube root of 8 is just 2. And we can't do anything with the cube root of 6, right? And the reason why is because you can't break up 6 into 3 things. So if you took 6, the best that you can do, oops, let's not use 1, is 2 and 3. And in order to remove anything, you would have to have not only a pair like you did with the square roots, you would have to have 3 of something. So that's how I know that the cube root of 6 is simplified just the way it is. So the final answer is just 4 times the cube root of 6. Let's try that same idea again. And the same numbers come up over and over and over again, right? You could do a factor tree for 108, but let me try and show you this way too. So here's 3 that's already on the outside of the radical sign. And one of the numbers that comes up a lot is 108. And the reason why is because 108 is 27 times 4. And we like 27 because it is a perfect cube. So the cube root of 27 is just 3. And then here we are with the cube root of 4. And notice that we can't simplify the cube root of 4 because the most we can do with it is get a pair of 2s. If we wanted to bring anything out, we would have to have 3 of something. So you simplify that to 9 times the cube root of 4. Okay. All right, I'm going to delete this section. Right. Okay. Oops. Actually, maybe I don't want to delete that section. Okay. Well, actually, we've already done that. We can delete that. Okay. Now what we have here, and I will write it, we've got radicals with variables. Let me type that. Okay. So it works kind of the same way. If you're taking the cube root of something, you have to have 3 of something in order to pull them out from under the radical sign. And remember, whenever you're taking the cube root of a negative number, your answer is going to be negative. So right off the bat, we can say that the answer is going to be equal to negative something, right? So we've got negative for sure. Now let's take 64. And recognize that the cube root of 64 is 4. So if we do the cube root of 64 times the cube root of, let's say, x cubed, so that's x to the 6th so far, x cubed, that's x to the 9th, and we'll just do x. With the y's, we could do a whole bunch of y's and stuff, but I'm going to show you a shortcut to that. So first of all, we know we have negative. So the cube root of negative 64 would be negative 4. And because I've got 3 x's here, 3 x's here, and 3 x's here, that means that for every 3 I have under the radical sign, I can bring 1 out. So I've got 1 for the ones I circled, another one, and another one. Now let's look at the y's. So we've got times, oops, let me go back to black. So we've got times, let's look at the y's. Let's see. So if we had y to the 3rd, so that would be 9. We need to get to 21, so we have to have 7 of these. Now, if you're savvy here, you're thinking, well, yeah, 21 divided by 3 would be 7, right? Okay, so now we have with the y values, let's see, we're going to circle all of these, right? 1, 2, 3, 4, 5, 6, 7. So we'd also have 1, 2, 3, 4, 5, 6, 7 y's out, right? Or if you simplified your answer, you would have 4x cubed y to the 7th. But a shortcut looks like this. We could say that this is equal to negative cube root of 64 times, what we're going to do is we're going to take this x to the 10th and separate it out. So we know that we can take x to the 9th, right? Because that goes into it 3 times. And we know that we're left with 1x by itself. Then if you take the y to the 21st power from the original problem, here's where the shortcut comes in. So we know this is negative 4. I should put a negative with that answer. We know that this, if this is a cube root, all you have to do is divide. So if you take 9, so we're going to say that the answer here is x to the 9 divided by 3 power. This is just the cube root of x, and this would be y to the 21 divided by 3 power. So you have to set it up so that you've got cube roots, right, together, or things that will give you 3 x's. So your final answer here, like I said before, is negative 4x cubed y to the 7th, and then we just have to just leave this alone because we don't have 3 x's. We forgot that on this answer. So in that problem, I showed you the long way and the shorter cut. You can do it either way, whatever's most comfortable for you. Okay, so let's see, how can we approach this one? Let's see, 81, I know 27 times 3 is 81, and I know that 27 is a perfect cube. So let's see. We're going to rewrite that as the cube root. Actually, maybe I'll write it down here. So this is, we know it's going to be negative. So it's the cube root of 27 times the cube root of 3. And I just know that 81 is 27 times 3. You'll start to get to know these numbers. Just maybe you will have started a factor tree and figured out what goes into 81, 3, and you'll start to recognize these the more and more we do these problems. And we'll be on this for a little while. Okay, so that takes care of the 81. Now, I know that I can't do anything with p squared because there's not enough p's to take out. I need 3 p's in order to take anything out. So I know that's going to be in my final answer. But q, what you could do is just jump to dividing. Since 12 is divided by 3, you could just jump to that. So let's see what we have. We have negative 3, since the cube root of 27 is 3, times the cube root of 3 times the cube root of p squared times q to the 4th. So anything that's left under the radical sign in your final answer is going to be under the radical sign, and anything's not is just going to be multiplied by itself. So we've got the 3 and the q to the 4th outside the radical, and we've got the 3 and the p squared inside the radical. Let's do a couple more examples. All right, so we could take, since 4 is divisible by 4, we could just say, oops, let me get that back. Let me get my pen back. We could say this is the same thing as w to the 4 over 4 power, right? Times, now we're going to split that 17 up. So we have v to the 16th power, and I'm using that because 16 divided by 4 is 4. And then you'd still have 1 left over of v to the first power. So what we have here is w to the first power, or just w, times v to the 16 divided by 4 times the 4th root of v. Can't do anything with v to the first because you'd have to have 4 of them to remove it. So simplified, this would just be wv to the 4th, since 16 divided by 4 is 4. And then we would multiply it by the 4th root of v. All right, hopefully this is getting easier for you. All right, for number 16, I'm going to first look at the number 48. Something that you'll start to recognize right away is that 48 is 16 times 3. So we can rewrite this as the 4th root of 16, which we know is a perfect 4th root, times the 4th root of 3. Now, since 8 is divisible by 4, we can just pull that out and say that's going to be 8m to the 8 over 4 power. But we know that there's not enough n's, right? There's only 3. There would have to be 4 to move anything out. So we know that has to stay in the radical, because you'd have to have n to the 4th at least, or a multiple of 4. So this has to stay in, because there's not enough n's. So from here, we're just going to simplify. Let's say we have 2 4th root of 3. Oops, let me make that a little neater. M squared. And we already said we had to leave this alone. Okay, so anything on the outside stays on the outside, putting it together. So 2 and m both move to the outside. And what's left on the inside is the 3 and the n cubed. All right, so just 2 more left here. All right, so 625 is a perfect fourth root. And you'll get to know this, right? Because you'll have tables in front of you and you can take a look to see if 625 is a perfect fourth root. So we can separate this out. The fourth root of 625 is just 5. And then we're going to take c to the 23rd and rewrite it as c to the 20th and c to the 3rd. And we're doing the 20th because 20 is divisible by 4, right? So we have 3 left over after we take as many as we can get. Now, what about the d to the 11th? Let's see. 11, you would say d to the 8th power, and then there would be 8, 9, 10, 11, 3 more d's left over. All right, now let's see what we do when we simplify this. So it'd be 5 times c to the 20 divided by 4. It's not very legible. Times the fourth root of c cubed. Can't do anything with that because we don't have enough c's. But here we can write it as d to the 8 divided by 4. Again, not very neat. Let me go back and do that. And then this, we can't do anything with it because there's not enough d's to come out. So let's simplify. We have 5c to the 5th, d to the 2nd, and then what's left under the radical signs? We've got c cubed and d cubed. That's as much as we can do. Well, this one's a little bit easier because we already know that 8 is divisible by 4, right? So we can take this whole thing, y plus 3, and raise it to the 8 over 4 power, which is equal to y plus 3 squared. And y plus 3 squared means y plus 3 times y plus 3. So we're just going to FOIL. So we've got y squared plus 3y plus 3 more y plus 9. Or y squared plus 6y plus 9. All right, guys, that's all I have for you today. There is some work on Schoology for you to do. If you have any questions at all, just email me and I'm happy to meet with you privately. It looks like I'll be back in business by Tuesday. So have a great day and I hope you had a nice weekend.